Okay, so good day, everyone. So our topic now is the chemistry of lipids, and this will be your first lecture in biochemistry. The lecture is divided into two parts. So the first part will be an introduction into lipids, one of the four biomolecules that you will be discussing in biochem. Now, we shall be classifying lipids, and then we'll discuss two examples of the molecules that belong to the lipid family, which includes the fatty acid and the triacylglycerol. And then the second half of the lecture will be dealing with the more complicated or complex lipids, which includes the phospholipids, the sphingoglycolipids, cholesterol, and steroids. And then we'll end the lecture with a discussion or introduction into lipoproteins. So let's now start with an introduction and classification of lipids. Now, lipids are a class of biological molecules. As a group, they have very heterogeneous structures, like what you see here. Some are linear, and then there are lipids which contain rings. Now, we group lipids together because of their low solubility in water. The reason for that is that the molecule is made up largely of hydrocarbons, and the more hydrocarbons a molecule has, the more nonpolar it is, the more hydrophobic the molecule is. It also is highly soluble in nonpolar solvents. Now, how do we classify lipids? Well, there are two main ways to classify lipids. Lipids can be classified based on structure, or they can be classified on the basis of whether they can undergo hydrolysis under alkaline conditions. For this lecture, we shall be classifying lipids based on structure. So lipids can be either simple or complex. When we say simple, they have components that are made up of simple constituents like fats, oils, waxes, and steroids. If they have components other than lipids, we call them complex lipids. Like phospholipids have components such as phosphates, sphingolipids, and glycolipids contain components like phosphate for sphingolipid and sugar for glycolipids. And then we have the derivative of lipids, which includes the hormones and fat-soluble vitamins. On the basis of whether they can undergo hydrolysis under alkaline conditions, there are only two categories here. Saponifiable lipids are those that can be broken down or hydrolyzed under alkaline conditions to yield salts of fatty acids. If they are not capable of undergoing hydrolysis under alkaline conditions, these lipids are classified as non-saponifiable lipids. So what are the biological functions now of lipids? So they do have diverse function, and one of the function is that they serve as metabolic fuel. As a matter of fact, fat is the most concentrated storage form of potential energy. So when we burn fat, it yields 9 calories per gram. So this is much more than what can be obtained when we are burning carbohydrates. Now, lipids are also very good insulator. As a matter of fact, fat is a bad conductor of heat, and thus it provides excellent insulation. They also provide mechanical protection. So adipose tissue, which contains a lot of lipids, provide mechanical padding to protect internal organs. Lipids can also serve as building blocks. Like some compounds are derived from lipids, and this would include, of course, hormones, vitamins, and secondary messengers. And finally, lipids have structural functions. Like lipoproteins are components of, are transporters of other lipids, so they're composed of proteins and lipids. And phospholipids are actually the constituents of the cell membrane. So the first lipid that we shall be discussing today is the most simplest of them all, and these are the fatty acids. So first of all, what are fatty acids? So this can be defined as naturally occurring carboxylic acid with an unbranched carbon chain. And usually they contain even number of carbons, but not always. So we have a typical fatty acid here. So the constituents includes the carboxylic acid, and this is the reason why they are referred to as fatty acids. And they do have a hydrocarbon chain composed of carbon and hydrogen. So these are the two essential features of fatty acids. Now, there's a lot of variation among fatty acids, and they can differ from one another based on the length of the hydrocarbon tail, based on the degree of unsaturation or the presence of double bond, and if a double bond is present, based on the position of the double bond in the chain. So fatty acids are said to be long-chain fatty acids if they contain 12 to 26 carbon atoms. And these fatty acids are usually found in meats and fish. Fatty acids are said to be medium chain if they contain between 6 to 10 carbon atoms. And finally, short-chain fatty acids contain fewer than 6 carbon atoms, and usually are found in dairy products. Now, the hydrocarbon chain, whether they are long chain, medium chain, and so on, can be either saturated or unsaturated. So palmitic acid is an example of a long chain saturated fatty acid. So it contains 16 carbons, and if you notice, the chain itself does not have any double bond. So this is one way to represent a palmitic acid. And this is another manner in which a palmitic acid can be represented, where the letter C and letter H have been omitted for simplicity. Now, if you notice, saturated fatty acids have a chain that is straight, and this can affect their physical properties. On the other hand, oleic acid is an example of a long chain unsaturated fatty acid. It contains 18 carbons, and right in the middle, you have the presence of double bond. Now, because of the presence of a double bond, it results to a kink. It's no longer a straight chain, and this can profoundly affect the physical characteristic of the fatty acids. So the molecules are farther apart from each other, and this results to a fluidity in its state. So just to recap, saturated fatty acids contain a carbon chain that are filled with hydrogen atoms. So there are no double bonds. Where can we usually find the saturated fatty acids? These are usually found in animal sources, such as butter, as well as in lard, and in tropical oils like palm and coconut oil. Now, because the chains are straight, they behave like crystals. So they are solid at room temperature, and they do have a higher melting point. On the other hand, unsaturated fatty acids contain a chain that lacks some hydrogen bonds, some hydrogen atoms, rather. So this means there is a presence of at least one double bond. So unsaturated fatty acids can be monounsaturated if they only contain one double bond, or they can be polyunsaturated if they contain two double bonds or more, like those found in corn, safflower, soybean, sunflower oils, and fish oil. Now, like what I said earlier, because the chains have kinks, the chains are farther apart from each other. Thus, they behave as fluid at room temperature. So they appear liquid at room temperature, and they do have a lower melting point. So we have here two examples of unsaturated fatty acid. Oleic acid contains 18 carbon, and in its chain, it only contains the presence of one double bond right exactly at the center. So this is a mono unsaturated fatty acid. On the other hand, below is linoleic acid, also contains 18 double bonds, but it contains two double bonds. So this is classified as polyunsaturated. So between the two, we can say that linoleic acid has more kinks, and therefore this has a lower melting point compared to oleic acid. Now, we can actually convert an unsaturated fatty acid to a saturated fatty acid. The process is referred to as hydrogenation. In this reaction, we can see that an unsaturated fatty acid is exposed to very high temperature in the presence of catalysts like nickel and hydrogen gas. So this reaction is called hydrogenation, and this converts the unsaturated fatty acid to a saturated fatty acid. Now, hydrogenation process does not just produce hydrogenated fatty acid. It can also produce some side products. This can include the trans fatty acid. Now, there's simply a structural rearrangement so that the double bond remains present, but there is a change in the configuration that we shall be discussing in a little while. So just to recap, hydrogenation can convert an unsaturated fatty acid to a saturated fatty acid. Now, what we desire is complete hydrogenation, where there is now the conversion of the double bond into single bond. However, that is not always the case. In the process of hydrogenation, we do have some side products, and this is the presence now, the conversion of the cis fatty acid to trans fatty acid. So there is simply a rearrangement of the hydrogen in the double bond so that they are now located opposite each other. Now, this trans fatty acid is actually bad for your health because it can raise LDL, what we refer to as the bad cholesterol, and lower HDL, what we refer to as the good cholesterol. And this trans fatty acid is associated with increased risk of developing heart disease and stroke, as well as associated with a higher risk of developing type 2 diabetes. So trans fatty acid is bad for your health. So one advice that you can give to your patient later on is to avoid trans fatty acid. And you can also advise your patient to avoid fatty acids that have undergone hydrogenation, because the hydrogenation process does not only produce saturated fatty acid, but as a side product, they can also produce trans fatty acid. So what is the difference between a cis and a trans fatty acid? Let's take a look at the cis form first. In the cis form of the fatty acid, the hydrogen are located on the same plane. And this results to a chain that has kink. So this is more liquid at room temperature. On the other hand, a trans fatty acid has hydrogen that are on opposite plane. As a result, we have a chain that appears to be straight. So it behaves like a saturated fatty acid. And this is a trans fatty acid that, like what we said earlier, is bad for your health. So we have more examples of fatty acid here: stearic acid, oleic acid, linoleic acid, and linolenic acid. Now, all these four fatty acids contain 18 carbons. But the difference is that stearic acid is a saturated fatty acid. It doesn't have any double bond in its chain, and therefore the chain is very much straight. Oleic acid contains one double bond. Linoleic acid contains two double bond, and linoleic acid contains three double bond. So we can more or less predict the behavior of this fatty acid based on the presence of double bond. Of all the four fatty acids, we can say that stearic acid has the highest melting point, because as a molecule, these molecules are closer to each other. They behave like crystals. So they are solid at room temperature, and they do have a higher melting point. Of all the fatty acids that we have here, we can say that linolenic acid has the lowest melting point. It's the most fluid, because if you have a lot of linolenic acid, because of the kinks, they are farther apart from each other. So the more kinks or the more double bonds you have, the lower is the melting point, and the more fluid the fatty acid is. So how do we name now fatty acids? Well, the term that we used earlier, stearic acid, oleic acid, linoleic acid, is referred to as the trivial name. But there's actually a systematic basis for naming fatty acids, and this can be based on the number of carbons. So let's start first with unsaturated fatty acids. So a fatty acid can be named based on the number of carbons on the parent hydrocarbon and simply add the suffix oic. For example, a saturated fatty acid that contains 18 carbon, like stearic acid, can be called octadecanoic acid. Octadeca means 18, and simply add the suffix oic. And what about for unsaturated fatty acid? Well, the system is still the same. The name's still based on the number of carbons, but what changes now is the suffix. If it only contains one double bond, the suffix is now enoic. If there are two double bonds, the suffix is now dienoic. Naturally, for three double bonds, the suffix is now trienoic. Let's start first with an 18 carbon unsaturated fatty acid with one double bond, such as oleic acid. The systematic name is octadece, which means 18, enoic acid. 18 carbon with two double bonds like linoleic acid can be called octadeca, which means 18, two double bonds, so dienoic acid. And finally, linolenic acid, three double bonds, 18 carbon, can be called octadeca, which means 18, three double bonds, so trienoic acid. So these are some examples. You can have a practice on them, like what we said earlier. Stearic acid, 18 carbon, no double bond, so the systematic name is octadecanoic acid. Oleic acid, 18 carbon, one double bond, 18, so octadecanoic acid. Linoleic acid, 18 carbons, two double bonds, so octadeca, 18, di for two, enoic acid. And finally, linolenic acid, 18 carbon, three double bonds, so it can be called octadeca, which means 18, tri, 3, enoic acid. Now, linoleic acid and linolenic acid are said to be essential fatty acids. Essential fatty acids are fatty acids that your body cannot produce, which means they have to be present in our diet. So we'll have more of that, essential fatty acids, later on. Let's go now to how fatty acids can be numbered. And there are two basis for numbering fatty acid. The first is called the delta numbering system, and the other one is referred to as the omega numbering system. Let's start first with the delta numbering system. Our example is oleic acid. The structure is shown here. Oleic acid contains 18 carbon. So if you use the delta numbering system, oleic acid can be referred to as 18 colon 1 delta 9. So what does this mean? If this is a fatty acid, oleic acid, if you count the number of carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, it contains 18 carbon. Colon 1. It means that oleic acid contains one double bond in the chain. And delta 9 refers to the position of the double bond. And where do we start numbering? We start numbering at the carboxyl end. This is referred to as the delta end. 1, 2, 3, 4, 5, 6, 7, 8, 9. Delta 9. What if you use the omega numbering system? So this is much simpler. Oleic acid is referred to as omega 9. Where do we start counting? At the omega end or the methyl end? So this is our reference point. This would be counted as number 1. The tail end is counted as number 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have another example here. Let's use the delta numbering system. Take note that the orange highlight here refers to the delta end. whereas the green highlight here refers to the omega end. So this can be designated as, if we use the delta numbering system, 18 because it contains 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 carbons. Colon 3 because it contains 3 double bonds. At what position? We start counting here. 1, 2, 3, 4, 5, 6, 7, 8, 9. 10, 11, 12, 13, 14, 15. So 9, delta 9, 12, 15. If we use the omega numbering system, this is much simpler. We simply refer to linoleic acid, linolenic acid as omega 3. 1, 2, 3. Now try practicing on linoleic acid using both the delta numbering system and the omega numbering system. If we use the omega numbering system, we start at the green highlight. And this can be referred to as omega 1, 2, 3, 4, 5, 6. So linoleic acid is an omega 6 fatty acid. For your assignment, try numbering this using the delta numbering system. Now, linolenic acid, omega 3 fatty acid, and linoleic acid, an omega 6 fatty acid, are both essential fatty acid, like what I have said earlier. This means that these two unsaturated fatty acids should be present in our diet because our body does not produce essential fatty acid. And where can we find these fatty acids? They can be found in plants, in oils, in nuts and seeds, as well as in whole grains and fish. So we should have a serving of plant oils, nuts, seeds, whole grains, and fish, maybe 2 to 3 times a week. What is so important about this fatty acid aside from being essential? So they play a normal role. They play a role in normal growth and development and may prevent heart disease, hypertension, arthritis, and cancer. So it is beneficial for your health. Now let's move on to the triglycerides, commonly referred to as fats and oils. Well, fats and oils are actually a mixture of many lipids, but the predominant lipid in fats and oils are triacylglycerol. So what is a triacylglycerol, or the major component of fats and oils? So these are said to be the fatty acid esters of glycerol. In other words, it's a combination of fatty acids bound to a backbone called glycerol. So the technical name is triacylglycerol. Now, what is the difference then between a fat and oil? Well, fats are usually solid at room temperature and are usually of animal origin. On the other hand, oils are usually liquid at room temperature and are of plant origin usually. So we have here the structure of a triacylglycerol. So the backbone, like what I said earlier, is a 3-carbon alcohol known as glycerol, shown in red. And sterified to it are 3 fatty acids. So the fatty acids can be either saturated or unsaturated. So how do we synthesize now triacylglycerol? So the components, like what I said earlier, are the backbone, the glycerol, plus of course, 3 fatty acids. So these fatty acids will be sterified to the backbone, forming now the triacylglycerol. And the process of bonding the fatty acid to glycerol is referred to as a dehydration reaction, where we remove the hydroxyl group here and the hydrogen here, liberated in the form of water to form an ester bond. Well, the process can be reversed, and the reversal of this process is known as hydrolysis under alkaline conditions. So that is called saponification. Now, a triacylglycerol can either contain saturated or unsaturated fatty acids. Let's compare the two. Well, so the triacylglycerol can either contain fatty acids that are purely saturated, and they can also contain an unsaturated fatty acid, maybe one or more. So what's the difference between the two? Well, if they do only contain saturated fatty acids, if you take a look, they are more compact. So they behave again like crystal, which means they are solid at room temperature and they have a higher melting point. On the other hand, in the presence of the double bond, because of the kink, the molecules are farther apart from each other. So they don't behave like crystals. So they have a more fluid state. So therefore they are liquid at room temperature and they do have a lower melting point. So triacylglycerol that are of animal origin are usually almost always composed of saturated fatty acids, whereas those that are of plant origins, those are oil, have more of the unsaturated fatty acids, and that's the reason why they are liquid at room temperature. Now, fatty acids, fats, and oils can undergo chemical characterization. So I will be presenting three. The acid number, something similar to the acid number, is the saponification number, and finally the iodine number. Let's start first with the acid number. This is defined as the milligrams of KOH, or sodium hydroxide, or any alkali required to neutralize the free fatty acid in 1 gram of oil or fat. So remember, oil or fat is actually a mixture of many lipids, which includes triacylglycerol and free fatty acids. In the acid number, what you're trying to measure is the amount of free fatty acid. So here we're going to neutralize the free fatty acid using either KOH or sodium hydroxide. So the process is called saponification. The result is the formation of soap. So the higher is the acid number, it means that there are more free fatty acids in the oil or fat. And the free fatty acid is what gives oil or fat its rancid smell, as well as its rancid flavor. Now, something similar to the acid number is the saponification number. So this is defined as a milligram of KOH or sodium hydroxide required to completely saponify 100 grams of oil or fat. So what is the difference between the acid number and the saponification number when the reaction is virtually the same? So the saponification number neutralizes all the fatty acids, whether they are free or bound to glycerol. So the reaction is the same. It's a simple saponification reaction. And finally, we have the iodine number, defined as the grams of iodine that can combine with 100 grams of oil or fat. So what is the significance of the iodine number? So this indicates the degree of unsaturation of oil or fat. So in this reaction, we have linoleic acid, which contains 2 double bonds. In the presence of iodine, the iodine is absorbed into the double bond, forming now a saturated fatty acid that contains iodine. We call it the stearate tetraiodinate. So how do we visualize the reaction? Now remember, iodine is colored violet. When it is absorbed into the double bond, the iodine is decolorized. So when a fatty acid decolorizes iodine, it means that there is the presence of double bond that absorbs the iodine. Now, what about unsaturated fatty acids? Unsaturated fatty acids, can they decolorize iodine? Well, they can't because they don't have any double bonds. So let's summarize what we have discussed today and end the first part of our lecture. So lipids are large heterogeneous class of biomolecules, and we group them together because of their hydrophobic nature. They have low water solubility, but they do have high solubility in nonpolar organic solvents. The first member of the lipid family that we discussed are the fatty acids. So these are defined as hydrocarbons with a carboxyl functional group. So the fatty acids may be either saturated or unsaturated, and the degree of unsaturation can affect the physical behavior of a fatty acid. And finally, the storage form of fatty acid is the triacylglycerol. So these are fatty acids esterified to a glycerol backbone. So if there are questions or comments, you can send your questions or comments via the official email, and I'll try to answer all of them. So let's end now the first part of our lecture, and we shall continue with the second part.